Welcome back, everyone. As you can see, it's a slightly different video setting this time. I'm not in the Felix Klein lecture hall anymore. The lecture hall is quite busy actually these days and also will be during the regular start of the courses. I'm still recording this a few days earlier. I will probably not be able to use this lecture hall all the time. So this time I borrowed a camera kit. Our faculty was so nice to get some new recording equipment for the start of the new term so people can record their own lectures, and this is what I did. I borrowed a camera kit and then sneaked through the building and searched for an empty room, and yeah, even dressed camouflage to match with the blackboard so no one will notice. I'm now in room A314 in the same building, and yeah, I'm using this to give a lecture. So I might alternate between the two recording settings. I might also go to a completely different room. It would be nice if you gave me a comment or in the Moodle discussion board or something, and if you could just let me know which of the video settings is better for you, as you think. So I think this should have a better video quality, but maybe the other thing is some advantages I can't see. But at least this time I have 4 blackboards, of which 3 of them should be at least visible. There's a stupid thing in the middle which is not removable, but yeah, I will do my best and hope that I will get get oriented with the blackboards and so can present the stuff reasonably to you. Okay, last time in the first section we just spoke about set theory, about sets and maps and very general things. Our next big aim, as already mentioned in the beginning, is that we want to give a formal construction and a formal definition of the real numbers that we all know from high school. This we want to now construct properly. It's not enough to have a set, but on the real numbers we have some additional stuff. Namely, we have computational operations. We have additions, we have multiplications. We can compute with real numbers. And of course, without these operations, there's no point in discussing these numbers. So what we need is a formalization of these operations, these mathematical operations, to more general sets. So this should be the aim of this section, which is called groups and fields, and I will define in a moment what this is. We want to equip sets with mathematical operations. And in this way, generalize operations like, generalizing addition and multiplication. Because when you come to think about it, addition and multiplication are actually the two key objects. Of course, you have subtraction and division, but subtraction is nothing but addition with negative numbers, and multiplication is nothing but division is nothing but multiplication with reciprocal numbers. So, in some sense, these are just secondary operations, and the really important things are addition and multiplication. So, this is the aim of this section. So, we make a big step towards having the real numbers, but can really define this formally. So, definition 124, we start with the first basic notion of sets with operations, namely the notion of groups. And what is a group? A group is a pair, which we denote as a tuple in some sense, and G and some dot. First of all, I have to apologize. Last time, I noticed how bad my English is. Because last time I called the quotation marks you put around something, so these things here, I called parentheses, which is of course nonsense because these things are called parentheses. These are quotation marks. Sorry about that. Similarly, I called these brackets special brackets because I was lacking the word. These are called braces. So sorry. Brace yourself for what's coming. We have a group as a pair, G and dot, where, very simple, G is just a set. And the dot is a map. This, of course, should kind of formally generalize as multiplication dot. This is why I called it this way. I could also call this differently. And what does multiplication do? If you think about it, you take 2 numbers, multiply them, so you take 2 numbers and get a new number out of it. So to generalize this, we want to have an operation which takes 2 elements of the set and gives out another element of the set. So this should be kind of the multiplication. This is the way multiplication or some algebraic operation here should behave. So this is a map, and not only a map, it should have some properties with the following properties. Okay, maybe start with the next blackboard because I want to get, there are 3 properties and I want to get them all on the same blackboard. So the first one I call G1, just to be able to refer this later on. And this is what we call associativity. Which means, we know for multiplication, the order of multiplication doesn't matter. So if you multiply 2 with 3 and then with 4, you get the result 24. So 2 times 3 is 6, times 4 is 24. But if you do it the other way around, if you first multiply 3 and 4 and then multiply with 2, you get 24 as well. So the ordering should be irrelevant. And this is something we need to formalize. And this is what associativity does, namely for all elements G1, G2, G3 from our set G, we want that the product, so I just will call this map dot product, although it's just technically just a map, G1 with G2, and then multiplied with G3, where these parentheses, these are not really parentheses, where the parentheses really show, we first multiply them and then multiply the result of this computation here with this element. This should be the same as doing it the other way around. So G1 and then first multiply G2 and G3, then multiply with G1. So formally this makes sense. This is what we want to have. This is what our formalization should do. Second thing, G2, this is what you can call existence of a neutral element. Namely, there exists an element, E, from G, such that G multiplied with E is the same as, the same, multiplying with E doesn't change anything. So G multiplied with E should be just G itself. And if you think about multiplication, this is what the number 1 does. So if you have the multiplication as we know it, and as we know it from school, 1 is the element with which you multiply things and don't change anything. So we demand that this exists. So G1 times E should be G, and the same should hold for multiplication from the other side. So if we take this multiplication, and this we want to hold for all G in G. Okay, and this E is then what we call a neutral element. Third thing that we want, the existence of inverse elements. So we want that every group element, so every element G of G, there should be a so-called inverse element. So there exists an element we call G minus 1 in G, such that G times G minus 1 should be just a neutral element. So some inverse of this, like for example, if you take multiplication in the real numbers, the multiplication of x is the inverse of x is the number 1 over x. If we exclude 0, I will come to this later, but this would be the formal inverse here. So or in the rational numbers, just the reciprocal of a fraction. So we want this to, just axiomatically, we demand that this exists. So G times G minus 1 is the neutral element, and the same for the other multiplication, if we flip the order, is the same as G minus 1 times G. So if you have some G and some operation dot, such that these things are satisfied, this is what we call a group. Additionally, if we have such a group G dot is called abelian, named after the famous mathematician Niels Henrik Abel, which then in English would be spelled as Abel and then abelian, or commutative. If the following holds, and this is something that's definitely true for the real numbers, but this doesn't follow from these 3 axioms here. Namely, if the multiplication of G times H is the same as the multiplication of H times G. So we can kind of modify it in this way. So if this holds for all G, H in G. So kind of the order in which you write it down doesn't matter. So not only this means that for a fixed order, the sequence of if we first multiply these elements or these doesn't matter, and here it really means that the order of these things don't matter. But there really exist groups which are not abelian. So groups which are not abelian, you can show this. Yeah. Let me just insert my favorite algebra joke at this point. Why did Gauss not invent group theory? Because he wasn't able. Yeah, sorry. Sorry about that. Okay, if we have a group, the map dot is then called the group operation. And E, as it's already in the title of this axiom, E is called the neutral element. And if it's clear which group we are considering, and if we know what operation is here, then we use just short notation. We just write G and ignore the dot when it's clear what we mean. So G for G, comma, dot. So this is something if it's clear, you can leave out. Okay, yep, I'll leave the blackboard like that. Okay, this is a group. Something I should maybe just mention, groups are really natural structure, and they occur in physics quite often. I think in your lecture course on theoretical physics you will also learn a lot about them. Because they occur everywhere where some physical system has symmetries, where some object can rotate, for example, and yeah, this is in classical mechanics one of the most important things, the rotations and so on. Then the rotations in some sense form a group. So kind of symmetries and groups are really connected very closely, and this is where you will see many examples of them. So I will only give one very simple example here, and you will see more advanced ones later in this course or in the theoretical physics lecture. Okay, because we don't know that many sets yet and don't many things, so I start with a very simple example which we've already used. Namely, not multiplication, but I take the integers and I take the operation plus. So, oops. This is not just, yeah, I've noted this like multiplication, but formally this is just meant to generalize some algebraic operations, including plus, and we will see that Z with plus is actually an abelian group. Okay, yeah, with usual, so plus is the usual addition, which I technically haven't defined, but yeah. So addition of integers, you know what it means. And we just have to think about it. First of all, we have the first axiom, associativity. We know from school kind of that addition is associative. So if we, in this case, this would mean if I have, maybe I read like this, G1 is true. Namely, this time it means if we have some, let's say N1 plus N2, and so we just have to replace this operation dot by plus N3. This we know that this is the same as N1 plus, and then here the sum of N2 and N3 for all N1, N2, N3 in Z. So this is what we know from school. So the order of addition, this is what associativity says. In this case, this doesn't matter. Okay, for G2, we have a neutral element for addition. The number 0. Adding 0 doesn't change a number. So E is equal to 0 is the neutral element. N plus 0 is the same as 0 plus n is just n for all n in Z. And now for the inverses. The inverse element of an integer n. Okay, what do we need? So we know that we want the number that we have to add to n to get to the neutral element, which is 0. So which do we need to add to n to get to 0? This is just minus n. This is minus n. So n plus minus n is minus n plus n is 0. And so this is why we have this inverse. And so this shows that this satisfies the axioms of a group, and it's abelian. This is also something very simple. We know that m plus n is the same as n plus m for all m n in Z. Again, here I'm technically relying on the addition for you to know this from high school, but we know that these properties hold. And this is, this shows that this is a very simple example of a group. Okay, the same, if now there would be people in this room, I would ask the question, what about multiplication? Is Z with a multiplication in a group? And it's not, because the inverse elements don't exist. The inverse element of an integer n would be 1 over n, which is not an integer. So it's not lying in the set that we are considering. We need rational numbers for this situation. So Z plus would not be a group. Okay, so much for that. Okay, some remarks. We can now see that some properties of groups already follow from these defining axioms, although it's just 3 little harmless axioms. This is now an example of how we can derive nice properties just from axioms. First of all, the neutral element of a group. Of a group G dot, right again, is unique. There is only one such element. Because here I just demand that there is the existence of a neutral element. There is some E such that this property holds, but of course a priori there might be more than one. So there could be several ones, but turns out this is not the case because we can just derive from these properties that there can be no two different neutral elements. And this is, the proof fits in one line, namely if E and E prime from G are neutral elements, so which a priori might not be the same, then what do we get? We get that E, since E prime is a neutral element, multiplying E with E prime doesn't change E. So this is the same as E times E prime. So this is because of the fact that E prime is neutral. But now we can argue the other way around, because we know that if we multiply something with E, this doesn't change the element, so this here must be the same as E prime, since E is neutral. So that's it. You have already shown that these two elements are the same, so there can be only one neutral element. Okay, a similar thing, which is also something you intuitively might assume, but which is not that obvious, namely the inverse element is also unique, so of a group element. So the inverse element of some G in G is also unique. And again, here we've only assumed by this axiom that there exists some inverse element, but a priori there could be more than one. And we can show that this is not the case. Assume we have two different, or not necessarily different, but if we have two inverses. So if we have H and H prime in G, and if they have the property that that are inverses, inverse elements of G, then we get the following. Okay, we start with H prime. Now we use the existence of a neutral element, because this is the same as E times H prime. So this is just group axiom G2. Now, we know that since they are by definition inverses, we know that the multiplication of G with both H and H prime is equal to E. So we can just replace this, simply by definition, by H times G times H prime. This is just because it's an inverse. So since H inverse, okay, can't write this small, you can read this anyway probably. So simply because H is an inverse, and so this product has to be E. But now we can just change the order of multiplication because of associativity, so because of group axiom G1. This is the same as H times G times H prime, but we had made the same assumption that H prime is an element, is an inverse of G. So this product again has to be E. So we get H times E, and since E is the neutral element, by group axiom G2, this is A. And so H prime is equal to H, and so there's only one inverse element. Okay, let me quickly erase the blackboard. As the next thing, I want to discuss two nice theorems about groups, which kind of also generalize properties of the real numbers and of the integers that we already know. The first thing, as a slight motivation, we know that some interesting thing holds in the integers. Namely, if we take minus n of some number n, which is the inverse of n in our new language, and take the inverse of this means minus n. And we know that minus of minus is plus, and that this is true in Z. So this would be the inverse of the inverse in our language. In the real numbers, assuming we have some x in R, so this was for n in Z, then we take some x in R without 0, then we know that 1 over x is the fraction which is the inverse of x. But if we now take the inverse of this again, so this would look like 1 over, and here 1 over x. So we just know from high school, maybe this parenthesis can be completely erased, so 1 over x, we know this is nothing but x. So again, the inverse of the inverse is the original element. And it turns out that this is a general phenomenon. Let me erase this to have more space for the general thing. That such a thing holds generally in groups. So we just need these few little axioms to get some crucial properties. So we start with some arbitrary group. Let G dot be a group. Then, and this is the first part here, the inverse of an inverse. So this is not denoting fraction or anything, this is this formal inverse that exists by the group definition. This is always the same as x for all x in G. Secondly, this is another phenomenon that I haven't mentioned here yet. If we take x and apply the operation to x and y, so a product or a sum or whatever, so x times y, and take the inverse of this product, this is the same as the product of the inverses, but the order is changed. In an abelian group, this doesn't matter, but here it's really the other way around. So this might not be the same as the other multiplication. So inverses and the operation behave nicely. So this holds for all x, y, in G. And it turns out this is actually not that hard to prove. Namely, we have shown that, that was the last remark, that inverse elements are unique. So we just need to show that that this here is really that x has the nice property to be the inverse of this element. And what do we need to show for this? So by definition of inverse elements, we have that x minus 1, so the inverse of x minus 1 times x minus 1 is the same as x minus 1 times its inverse, and this is the same as the neutral element E. So we have seen that inverse elements are unique, so we only need to show that x has this property, that x fits in here if we replace this here by x. But this obviously does, since x minus 1 is the inverse element of x, we know that x times x minus 1 is the same as x minus 1 times x equal to E. So replacing this by x really shows that this fulfills this equation. So then we already know by the, this is basically remark 126b, that x is, so the uniqueness of inverse elements, x is the inverse of x, which shows part A. To prove part B, it's not that much harder, because again we need to show that this has the right property of inverse elements. Namely, we compute for all group elements x and y, that if we take x times y times this element, that is our candidate for the inverse. Okay, we've got this, and we need to show that this gives the neutral element. And here we can again use the group axiom that these parentheses here actually don't matter, because we have seen the ordering doesn't matter. So by group axiom G1, associativity, this is the same as x times, let's do it explicitly. We can just shift these brackets, namely this is the same as this multiplication. So if we look at this, and this as three elements of the group, we have just changed this ordering. And here again, we can now, inside these bigger parentheses, we can change the position of these smaller parentheses. This is the same as x times y minus 1 times x minus 1. And we know here now that this is a neutral element. So this is the same as x times e times x minus 1, but we know the neutral element doesn't change the element by multiplication with the neutral element doesn't change the group element by property G2. So this is the same as x times x minus 1, which is indeed e. Okay, and the other thing that we need to show, so this is one property of the inverse, but completely analogously, so I won't do this computation now. One shows that the other way around, y minus 1 times x minus 1 in parentheses times xy, x dot y, that this is indeed e. So again, we know inverse elements are unique. So this would be again remark 126. Yeah. B. We get the claim that x minus 1 dot, y minus 1 dot x minus 1 is the same as x times y to the minus 1. And this is what we wanted to show. So a really crucial property, and the proof fits within a few lines, which is a nice, nice thing to have. Another nice thing, we want to solve equations, of course, in our sets of numbers that we want to study later on. And that we can do this is also a general thing we can do for each group, and so we prove a very basic theorem, which looks almost trivial, and the proof is also not that hard, but it's important to notice. If we have a group and we have two fixed group elements, A and B, then we can study the equation A times x equal to B. So this generalizes some standard equations from mathematics. And this equation with x as a variable, this has a solution, and this has a unique solution. This has the unique solution. X is a to the minus 1 b times b. This is obviously true if this is just multiplication of real numbers, and if we exclude 0 from everything, or if we take addition, here is an operation inside of the integers and so on, then it's clear that also this has a unique solution, but this is a phenomenon that really is inherent in the group definition. Okay, proof of this. First of all, that this is indeed a solution. This is easy to see. I mean, this is clear that a minus 1b is a solution, times b is a solution. Conversely, now we know this is a solution, but now we need to show that if we have some solution, it coincides with this one. So conversely, if we have some element x, if a times x is equal to b for some x in G, then we know that multiplying these things with some elements doesn't change the equality between these things. So we get, if we multiply everything with a minus 1, we get that a minus 1 times, and now we have to put the parentheses in here because we, first of all, we have to respect the order here. A to the minus 1 times a times x is a to the minus 1 times b. But again, since we have a group, we have associativity, so we can again reorder the parentheses. So we can move them to the front and first multiply these first two things. So this is again G1, and we get A minus 1 times A times X is equal to A minus 1B. And yeah, we know that this is the neutral element, and Newton multiplication with neutral element doesn't change anything. So this is equivalent to X is A minus 1 times B. And this is what we need to show. So these are some very, very basic and elementary facts about groups. Now we could kind of go arbitrarily deep into the subject, because group theory is an important part of mathematics and it's a whole research direction. So I can do incredibly many things with groups, but I don't want to do this because I don't want to distract us from the aim of constructing the real numbers. So I will not go further into bigger detail on abstract groups, and also you don't need this at the moment. So this is just some very basic overview of group theory, of groups. Okay, so we've now generalized these algebraic operations. We can generalize multiplication and addition in this joint framework of a group. But there's something else we need, because on the real numbers we have both addition and multiplication, and we want them to interact in a certain way. So we have some computational rules that hold within the numbers that involve multiplications and addition, like the law of distributivity. And this is what we next want to generalize. So we want some set which has two different operations, like addition and multiplication, which behave nicely. And we again want to define this just axiomatically. So yeah, let me keep this on the board. So next aim, study sets with two operations which generalize, so generalizing addition and multiplication. And we want these two separate operations. In some sense, let me just say this very roughly, they should behave reasonably with respect to each other. So they should not just be two separate operations that are not connected at all, but we want them to behave reasonably in some sense. Okay, and before I do this, I think I'll clean the blackboard so I can give it a fresh start. Okay. Next we define the second part of the headline of this section, namely a field. And this is precisely a set with two operations that behave reasonably in the sense that I just sketched. Okay, definition 129. A field is a triple. So we have K, which is again a set. We have an addition and a multiplication. So formally just two operations where K is a set. And we have plus and dot as maps which take two elements of the field. So two elements of K and return an element of K. So where this is a set and these are maps, such that the following holds. We have three properties, axiomatic again, K1, K2, K3. K1 is just that K with respect to addition is an abelian group. Okay, this is what we've seen before, so this is what we want to have. Then we want the multiplication to have the same property, but just almost the same. Namely, we want K star dot to be an abelian group. Where K star is just almost everything, but we just remove 0, where 0 is the neutral element of the addition plus. So where 0 is the neutral element of this addition operation. So apart from that, this thing with dot should be in a abelian group as well. So we have these nice computational properties. And the third part, this is now the interaction between these two. We want distributivity. And if you remember this word from high school, maybe it was used there. We want that x times a sum of two elements, x times y plus x times, and then parenthesis, y plus z, so first addition, then multiplication. This is the same as x times y plus x times z. And this we want to hold for all x, y, z in K. So this is the way we want these operations to be linked. They should behave in this nice way. And this is what we know from, of course we know the real numbers from high school. This is the way we always did arithmetic, so we can just use this rule here. Yeah, but this, so we want to hold in this very, very general abstract way. Okay, yeah, then some notation that we just use to keep things a bit short. So first of all, we call, I mean, this is just two operations, but just formally, I will always call plus the addition of K and dot the multiplication of K. This is really fascinating. We have some abstractly defined operations, but we can almost do the same arithmetics as in the real numbers. Just by some very simple rules. Yeah, okay. Yeah, denote, this is what I already had, the neutral element of the addition by 0 and the neutral element of multiplication always by 1. Neutral element of dot by 1. So this is what we kind of define 0 and 1 in this way, which looks a bit awkward, but it really works out nicely. And some shorthand notation. We just write xy instead of x dot y to denote multiplication, as we used to do in the real numbers in school when we still knew what the real numbers were and weren't confused by this university teacher who tells you different things. Okay, then we want to denote x minus y. This should be, as we are intuitively using, x plus the inverse element of y with respect to addition minus y. So this is just shorthand notation for this. And so this is what we want to hold for all x, y in K. And we want to denote fractions, namely we want to denote x divided by y. So what is this formally? This is just 1 over y is the inverse of y with respect to the multiplication, which is how we use usually this notation. So this is precisely what we want. This should be x times the inverse of y with respect to multiplication, and this now for all x in K, and now y is not 0, so y in K star, because only in K star we have an inverse by definition, because K star is an abelian group with respect to multiplication in this setting. Okay, and also short notation, we don't, if we write down the field, we don't, short notation. We don't want to write down the operations all the time, so we just write K instead of K plus dot, all the time. So this is just to abbreviate everything. So and if it's clear which plus and which dot we are referring to. Okay, so one may ask now, we have these group rules, so they give us associativity and everything, and inverses and everything, and we have this distributivity. So if we have a field, do we already have the real numbers? And the answer is no, because I can give you a very simple field, which turns out not to be the real numbers. Example 130, and this is again a quite unprecise definition. I will define this more properly later on. Namely, I define Q, the rational numbers, formally as the set of expressions P over Q, where P is an integer and Q is a natural number. So this is the set of rational numbers So just formally as the set. And so now I need to define addition and multiplication on them to make them a field. And this is how I want to model the, these expressions such that we want the usual reduction rules to hold. So we want that a times p divided by a times q is the same as p over q, and that this holds for all p over q in q and a in n. So this is reduction of fractions. So this is what we also want to formally hold. So on this set of these expressions, we need additions and multiplication. Let me just bring this into a reasonable ordering. Okay. Namely, we consider, let's do first multiplication because it's simpler. The multiplication of fractions, what do? We take two of these fractions and get a fraction as a result. Simply by saying a over b times c over d should be just multiply numerator by numerator and denominator by denominator. So ac over bd, where this is just the usual multiplication in z respectively in n. And the addition, this is something where already some people have problems with adding fractions. The formal rule looks like this. We take a over b plus c over d. So this is defined like this. And this is defined, so by bringing these two fractions onto the same denominator, so expanding this fraction to the same denominator and then add the numerators. This means that this is the same as AD plus BC divided by BD. This looks mysterious, so you try to compute some examples and remember how to use fractions. I mean, this is basically just abstractifying the standard use of fractions as you were used to. Okay, then it turns out, which I won't compute, but this is something you can really check using these rules, that Q with respect to addition and multiplication here is a field. So here you can really formally compute that distributivity holds, that these, that for example this is associative, is not that trivial. I mean, it's just a long computation, but it turns out that it's really the same. So it's really working. This is a field, and we know that the inverses of these elements, I mean 0 and 1 are then clear, and we know that minus p over q, so the additive inverse of p over q, is just as a fraction minus p, so this is again an integer, so by definition this is again a rational number as I've defined them as a set, minus p over q for all p over q in q, and the multiplicative inverses, p over q to the minus 1, this turns out to be just q over p for all p over q in q with p in n, otherwise this doesn't make sense. And if p is negative, you can just move the sign somehow so this is not too complicated. Yeah, this is, yes, this is how we can use the denote the inverses and so on. So, yeah. Okay, so this is what I won't check, but this is kind of the motivating example here. We know from high school, and as we will maybe discuss later a bit, that this field is not the complete real numbers. We have the real numbers are kind of, we have several real numbers like the square root of 2 or something which will pop up later that cannot be described as a rational number. Okay, but we now investigate some field properties. Okay, remark 131. First of all, since K plus is an abelian group, and this is something I just want to mention because one needs to realize that this is already following from what we have. Since it's an abelian group, theorem 127 implies, this was the theorem about inverses. And the inverse of the inverse is an element, this is what we had, and so with respect to addition, this means that in general minus x is always x. As I mentioned before for the integers, what we knew, this really holds always in the field. Minus x is x, and minus x plus y this would be the inverse of x associated with y by some operation. This was then given by minus y minus x, or plus minus x. And here we can, since it's an abelian group, we can change the ordering. So this is indeed the same as minus x minus y. So this is kind of a sanity check. The previous computation rules that we knew intuitively, they hold here in arbitrary fields. So we see that this is really, making sense. And this for all x and y in K. Okay, in the same way, Theorem 128 was about the uniqueness of solution of certain equations. And with respect to this operation, this implies that a plus x equal to b, this has a unique solution, which we know as b minus a, which is, this is a solution. So this has the unique solution x equal to b minus a. So this is another sanity check. Also this computational rule, this makes sense. So I hope you get more comfortable with the notion of a field, as you see that several roots that you already knew also hold there. Okay, here we assumed with multiplication that K without this element 0 is an abelian group. And it turns out that you can't really include 0 into there because multiplication with 0 is something not that good. Okay, if we have an arbitrary field, K plus dot a field, then if you multiply an element with a 0, you always get 0. This holds for all x in K. So another sanity check. This is something we know from the real numbers, so this behaves nicely. So in fact, all these rules now, when we introduce the real numbers formally, we have already proven by these things that all the computational rules that we just used intuitively in school, that they are really formally correct. They kind of really constructed things from scratch, and all the rules that we used are holding in this case. Okay, for the proof I need some more space, so I'll wipe out.